We are Team Cyborg from Group 5 and we are conformed by Alessandra de Subeldia, Cecilia Padilla, Ángela Garcia, Amanda Lopez, and Kevin Montero. We'll be presenting binomial theorem applications for the second partial project of trigonometry.
The first thing that you must do to solve this problem is understand it. It is also necessary that you investigate and comprehend the binomial theorem. The second step is to analyze the exercise and see how it relates to Pascal's triangle. Third, you have to substitute the values of the coefficients based on the row, which is the power of the binomial that you need for the Pascal's triangle. Fourth, with each step, you decrease the power of the x's and you increase the power of the y's. This is all based on Pascal's triangle and the binomial theorem. The fifth step, after completing this procedure, is that you must do multiplications and elevations to obtain the exact result. And the sixth step is only if the problem asks for a certain term, you have to count each term until you find the one that you need.
The French mathematician Pascal created this easy method in order to determine the binomial coefficients. In this case, we can observe that 1 plus 1 creates the number above it, 2, and 3 plus 3 creates 6, and 3 plus 1, 4. This method helped us to explain the binomial coefficients. Here we can observe that in row 0, we have that the coefficients of A are 1, as in here. In row 1, we have that the coefficient of A will be 1 and 1. In row 2, it will be 1, 2, 1, as in the Pascal triangle, and the sequence goes on. In this triangle, we can only observe a piece of it because the numbers are infinite, and it can be explained in this way.
Now I'm going to explain how the binomial coefficients relate to the Pascal's triangle. Here in this expression, we can observe that the coefficient of A, here in this case, is the same as in the Pascal's triangle, in the third row, as in here. And the first coefficient is 1, as in here, 3, 3, and 1. And in this expression, the variable b starts in 0 and it increases in 1, 2, and 3. And then here we have the binomial theorem. The binomial theorem is an equation that is used to expand a binomial to some degree. And here a plus b to the n degree is equal to, here we use the sigma notation. The sigma notation is a Greek number that is used to put the k starting value, in this case is 0, the n final value, and n what to sum. And here what to sum is nk times a to the n degree minus k times b to the k degree.
Now, in problem A of our project, we have to solve the binomial x minus 2y at the 7th power. Now, to be able to solve this, we have to use a theory that my two classmates gave before. So we use the Pascal triangle and the binomial theorem. So we have the power 7, and this applies only to x. So here we have x to the 7th power, and first, y starts out being 0. And we use the coefficients from the Pascal triangle, which in this case is still 0, or 1. Then we go to the next part in which the power of x decreases and the power of y increases. This is why it goes up to 1. And now we take one of the coefficients, the next one of the 7th row of the Pascal triangle, and it would be 7. And this is how we go throughout the whole problem. Here the coefficient goes up to 21, x decreases, and y increases to 2. We do this until x disappears, it gets to be 0, as y used to be at the start, and this one gets to be 7, which is the highest one that we got at the start. Now that we have this, since this has a coefficient, if it didn't have a coefficient and it were just 1, we could leave it like this. But what we have to do now is that, for example here, we would have to do 2 at the second power, which is 4, multiplied by 21. And that's how you get each of these coefficients, which are much larger. So what you do is that you elevate it to the power and multiply it by the coefficient that was already here. And this would be our final answer for problem A. Now, to solve the problem B of our project, which is the binomial a to the 2/3 power plus b, all to the 20th power, we also have to use the Pascal triangle in the binomial theorem. Now, if we have 20 as our power for the whole binomial, that means that we will be using the 20th row of the Pascal triangle, and that's where we will be getting our coefficients. So, first of all, we have to do the same thing that we did in the last one, where the a is going to decrease from 20 down, 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 and y, which would be b, will be increasing until a disappears, as it did in this case. The reason why these exponents are larger and different than the normal 20, 19, 18 is because they have to be multiplied 20 by 2/3 or 17 by 2/3, so they became fractions. The whole expression, the solution of the problem, is very large. So we decided just to show the first 4 terms and the last 3. What this problem asks for is the last 3 terms of this expression. So the last 3 terms, which are already simplified, and the multiplications of this one times this one are done, is this one, in which a disappears because it turns 0. Now, for the solution of problem C, which is the binomial x minus 2 all to the 25th power, we are also going to use binomial theorem and Pascal's triangle. We have 25th power, so we're going to be using the 25th row of the Pascal's triangle. Here we will have first an x, the 25th power, and we will have 0 for the y side. Next, as we have seen before, the power for x will decrease to 24, and y, which in this case is minus 2, will increase 1. That will happen throughout the problem. 23 for x, 2, it keeps decreasing, and x keeps going up in y. And the coefficients are based on the row, so for x it's 25, then 300, 2,300. Since we are on a very low row of the Pascal triangle, the coefficients are going to be a lot higher than they were at the start. Now, over here, we skip this part because it's a lot of procedure that we have in the document, but we're not going to explain it here. Here would be the last part, and they ask for the 24th term. But we can't give them the 24th term yet because we haven't simplified the expression. If we have a coefficient here, this would have to be elevated to the 23rd power. And here, minus 2 would have to be elevated to 2, which would be 4. So once you do all of that procedure, you would get the last 3 terms, and this would be the 24th term of this binomial.
¿Me estás poniendo?
¿Quieres que lo haga desde arriba?
Ahí ya.
Pero
Ya,
¿lo
ya
quiero
está.
volteado? Ah, ya.
Empieza, 1, 2, 3.
This project helps us analyze the relationship between a binomial theorem and a Pascal triangle application, such as expansion of binomials and combinations. Also, we notice that Pascal's triangle is a great tool for solving a real-life combination or probability problems because it is just pattern of sums. Now we are able to comprehend and obtain results in 2 different ways and apply them to everyday situations which we will most likely encounter in the near future. Thank you.